Excited to welcome you all to this exciting session, Machines of Vision, from functional to AI diagnostics. Today we embark on a journey through the fascinating world of medical. Grateful for your time and expertise. Grateful for your time and expertise. We are also honored by the presence of Professor Saroj Jayasinghe, whose leadership and vision in the medical field inspire us to explore new horizons where science, technology, and patient care meet. Thank you, Professor, for joining us today. I also extend a very warm welcome to all the engineering undergraduates, medical undergraduates, academics, professionals, and enthusiasts present today. This evening will not just be about listening, it will be about experience. I encourage all of you to actively engage, ask questions, and of course, make use of the hands-on AI.
The medical faculty, science and technology community for organizing this workshop, because this is a much needed collaboration for the country at this time, the collaboration between engineering and medicine. So on behalf of Moratuwa engineering faculty, I would like to thank for your community, and also I would like to welcome all the engineering faculty and medical faculty undergraduates, as well as professor for this moment. Okay, let's go on to the workshop procedure. So here today we are going to give a basic understanding about medical imaging modalities to you, such like X-ray, computer tomography, CT, then nuclear imaging, MRI imaging, and ultrasound imaging. And after that, about AI trends in the medical imaging, like the AI-based classification, diagnosis techniques in medical imaging, and yeah, we have some hands-on experience practical arranged to this session as well. So okay, today this workshop will conduct by me and Senul, and also from Hansa. They are all graduated from Moratuwa engineering faculty. So now I'll move to the first session of this workshop, X-ray and computer tomography. Okay, first of all, I have a small question. Anyone know what is this image? Does anyone know? Yeah. This is the image of world first X-ray. Actually, it's not intentionally made image. According to the sources, it's like accidental image. So this image is, as I can remember, Anna Braith's, the William Röntgen's wife. So as you can see here, so here the X-ray is basically for imaging our bone structure and such heavy, dense muscles. Okay, so here, when I give you an introduction to X-ray, the X-ray is basically a 2D projection of 3D data. It means if you have a 2D object, the X-ray will project it to the 2D plane. Okay, as you can see here, the human head is a 3D object, so X-ray will project it to the 2D surface, and you can take this 2D image. So William Röntgen is the person who invented the X-ray, and for that invention he won the Nobel Prize in 1901. Okay, so these are very great inventions, but every great invention comes with how would I say, sacrifice. So all his lab workers, his wife and he died because of high radiation exposure. I think you know the background, right? So but now X-ray are very controlled and very safe. So no, there's no point to worry. So next, okay, let's go to basic block diagram of X-ray. So as you can see here, here this is the cathode. Before that, I'll briefly say about some properties in X-ray. You know, X-ray is electromagnetic waves, right? So you know electromagnetic. What is the electromagnetic? It has electronic as well as magnetic field in the wave. So for generate this electromagnetic wave, we call X-ray. We have this X-ray tube. Okay, in X-ray tube there is a cathode as well as anode. Okay, in this cathode we apply a voltage to this cathode to generate we call electrode beam. Electrode beam means when we apply voltage between like we would say metal, what happened? The metal get heated. Okay, because of this thermionic emission, we call it thermionic emission. So then electrode get released. I think you all study this in your O levels, right? O level chemistry, the first lesson as I can remember. So then that release electrode get hit to this target. Target means anode, right? So then what happened? When some object go and hit to another object, that traveling object have very high velocity, it decelerate because of that impact, right? So in here also, because of that impact, those electrode get decelerate. Then according to energy conservation, what should happen? The energy should convert to another form, right? That velocity should convert to another form. So that form is 99% heat and 1% X-ray. Okay, so basically the major part of this energy convert to the heat, and only 1% of that energy convert to the X-ray. Okay, so so these are the three steps: electrode generation, electron acceleration, and X-ray production. So I think you have very basic understanding about X-ray now. So is there any question about this process? I think you don't have a question. Okay. So next I would like to ask, like if this is a heated filament, right? In cathode, I mentioned that we apply voltage to the cathode and it get heated, and then the electrode get hit to the target like anode. So what happened in the anode side? 99% of the energy converted to the heat, then anode can like get heated and liquefy, right? So to avoid that, this anode is rotating. So because of the rotation of the anode, the target is always varying. So the heat is evenly divided through the anode. So I have a small video about that X-ray generation. Oh, it's loading, sorry. Okay, as you can see here, the electrode beam get hit to the anode, then X-ray photons are released. Because of that impact, the anode is get heated. To avoid anode liquefying, the anode is get rotating, right? So this is the basic summary of X-ray production. So now there are we will go to the X-ray system. So the first block of the X-ray system is X-ray tube. Okay, if we need to X-ray, we need to generate X-rays. So the X-ray tube is the mandatory. Next, for use this as for the medical purposes, we need few other systems for these X-ray machines. The first one is collimator. Collimator means you can like imagine like if you have a light, if you turn on this light, the light rays go everywhere, right? So you can like in here also the light rays go everywhere. So in X-rays also, when X-ray generate in the anode, that rotating anode, the X-ray go everywhere. So it's not helpful for medical imaging because X-ray go everywhere is the one thing is it's not safe because of the radiation. The another thing is like we can't target a specific body area to a specific body area. So for target this specific body area, we have this collimator. Collimator means like small window shape object, right? So that's basically what is a collimator. Then we have anti-scatter grid. What is the scattering? Do you know scattering? Scattering means like basically you know the laser wave, laser beam. It's travel through a straight line, right? But light and other electromagnetic waves, they can travel like this way, this straight line as well. For every different way they can travel. So if there is a beam like this, travel like this. So if there is the person is here, let's say we are going to image a person born. So X-ray beams are travel in another angle. Would it be helpful? No, right? Because it go to another place and give a faulty image. So avoid those scattering effect. We use this anti-scatter grid. What it does is this basically made of lead. You know, lead is absorb electromagnetic wave, right? I think you know that. So because of this lead plates, these scattered waves absorbed by the grid and only straight lines pass through the detector, right? Okay, that's the another essential object. Next, okay, I think this is clearly visible to you. This is the image that took without using the grid. This is the image took with the grid. Can you see a difference? There are more details in here than here, right? There are a lot of noise in this image. Okay, so this is the use of anti-scatter grid, and every X-ray machines nowadays have this anti-scatter grid. Because of that, the X-ray have good quality. And also next we have detectors. Detectors means like where the image formed, right? So here when it come to detector, I think you all have seen these systems, detectors and other stuffs. But when it comes to detectors, in old time we used, not actually we, the medical imaging system use X-ray films. You have seen X-ray films like that black color thin sheet that have X-ray. So those are now replaced by digital detectors. So what digital detectors does is there are two way of conversion: indirect conversion, direct conversion. So I'll explain this briefly and slowly. So when it comes direct conversion, there are scintillators, means like you know sometimes electromagnetic radiation can convert, some object can convert electromagnetic radiation to light, right? So there are some specific materials that have used in these detectors like CSLTL. The name is thallium doped cesium iodide, right? I don't remember those stuff. So these objects are in the detector side, so in this plate. So those objects, like those are in array, okay? It means let's say there are 1,000 detectors in this side and 1,000 detectors in this side. Not 1,000, like let's say 100 and 100. So altogether there are 100 by 100 detectors. So when X-ray hits those detectors, those are generated energy. Energy means light. Then by using photodiodes, you know, we can convert that light source to a voltage source. Then we can form the digital image. The direct conversion means they are not using this detector like scintillators. They directly convert X-ray to the voltage source. But this is not very accurate. This is the main indirect conversion is the mainly used method in image formation. So next, let's move to drawbacks in X-ray. So when it comes to the muscles and fat, can we image muscles and fat using X-rays? No, right? Only bones. Can we image muscles and fat? No, right? So, and also, if you take look at in here, there is a bone, tissue, and air, same thickness, and here different thickness, same material. So, all two image form a same X-ray image. You can understand this, right? So, how can we differentiate these kind of things? Also, I didn't explain this. So there is three objects in here: sphere, triangle, and rectangle. When we take X-ray of these three all together, it forms single image, right? So because it's 2D projection of 3D data. So for overcome this challenge, human have developed the X-ray to computed tomography, CT scanning, right? So here what it take is we are taking X-rays from every direction, like by changing the angle of the this is X-ray tube and this is detector. So we rotate this X-ray tube and detector, then we take images, and we then after that we reconstruct those detected images. I said reconstruct, so I'll let you in future slide I'll explain what is reconstruction in CT scans. So I said in CT scan the detector and the X-ray tube is rotating, right? So have you ever seen a CT scan rotating scanner? So actually it's rotating very crazy speed, so you can see here. Maybe if patients know this is rotating this much of space, this speed, they will not go into CT scan, I think. It is. Yeah. As you can see here, the detector and X-ray tube all together rotating in a very fast, and then the X-ray tube and detectors aligning perfectly because of the instead of rotation is doesn't matter because tube and detector in direct line. So when it rotate, it takes image throughout the object. Then it form, let's say this is the object, then it form an image like this. You can see, we call this cyanogram. So there are 3 dots in here, right? 1, 2, 3. So for all 3 dots, it has 3 cyanogram here. So then we use, I don't know, you know the Fourier transform? There are transform like that. Fourier transform means in signals we convert time space data like sinusoidal waves into frequency domain by using Fourier transform. They are like transform from one domain to another domain. So these cyanograms we can convert into image by using those transforms like this. So if you image a brain, you get something like this. Then we have to post process to reconstruct the image. Okay, this is the computed tomography. Okay, now let's move the what are the latest development in CT. I think you know there are portable CT scanners now, right? So these scanners can move from one place to another place. Like there are teleclinics, right? Some medical team go to the villages and do some medical, I don't know, whatever. So there are CT scanners for specially designed by portable activities, and also there are AI integration stuffs in the CT scanners. Something like smart protocoling. You know what is protocoling, right? When body region is differs, the CT protocols, there are different protocols for CT scan. If we are going to image chest area, we have to follow different procedure than imaging the brain, right? So those things the now automated by using AI integration. And also there are image reconstruction and quality assurance by using AI tools as well. From that, the X-ray part and CD part is over. Now let's move to the ultrasound part. I would like to invite Hansa for ultrasound imaging, covering the ultrasound imaging.
Okay, thank you, Ravindu. And I'm Hansa Marasinghe. I'm going to talk about ultrasound part. And so from the imaging modalities we are talking today, ultrasound is the simplest one. So in ultrasound, what we are doing is we are using sound waves to see inside the body. And usually we hear from 20 hertz to 20 kilohertz. So more than that is ultrasound. Because of we are using higher frequencies, it's called ultrasound imaging. And also compared to X-ray and CT, it's safe because we don't use any ionization radiation. And main drawback is it cannot go very deep into the body. So if I recap a bit about what we have to take home from these points, it's very safe. If we can image every part of the body using ultrasound, it would be very great. But the thing is, ultrasound cannot penetrate too very deep into the body. Next, I'm going to talk a little bit about the working principle. So I think most of you have experienced this phenomenon, like hearing echo when we are in a very confined space, or if we have a very large wall and we shout at it, we can hear the echo if the right conditions are met. So here I have a simple question for you, like boy is shouting and he hears his echo after 4 seconds. If sound is traveling at 100 meters per second, what's the distance to the wall? I think it's a very simple one. Can anyone answer?
200 meters.
So it's 200 meters. The thing is, using this principle, we can find the distance to object. And even like this is true, like we can even see the distance, but because of sound waves can go through our body, we can find the distance inside our body. Next one is a slightly elevated one of previous question. Like if we have two walls and we hear two echoes, one echo after 3 seconds and another one after 4 seconds, what's the distance between two walls? Mm. 50 meters, right? Yeah. So even there are multiple objects, we can measure the distance. And one thing, I also have mentioned here, the second echo, we hear a little bit damped version of the echo. Why is that? Because when sound is traveling longer distance, it's getting dispersed and energy get less concentrated, and we hear less intensity sound. That's why it's getting damped. This is a not really good thing for ultrasound, because what we ideally want to do is identify different kind of materials and what are the distances to those materials, right? In tissues, different areas of tissues, and what are the distances. If the same, and to identify that, what we usually use is, to identify the distance, we take the time. and to identify the kind of tissue, we use the intensity. So if the same kind of material give two intensities, that won't be a great thing, but we in the algorithm we are running inside the ultrasound machine, we compensate for this one. Yeah, this one is also about that, like if I have a brick wall and a metal wall, echo I am hearing from metal walls is a little bit louder because it reflects most of the energy we are giving in that way. So we hear a little bit louder echo, and like that, tissues we have inside our body, they reflect sound waves in different amounts. So we can identify mainly two categories, like strong reflectors. Usually, I think because you are medical students, most of you can remember this as a rule of thumb. Higher density tissues, they reflect more sound waves. So if the higher intensity echoes we are getting, we show those as lighter color, in like close to white in the ultrasound image. And weak reflectors, they are a little bit darker in the ultrasound image. If you next time when you are seeing an ultrasound image, you can notice this one. That's the basic working principle of ultrasound. Like, we measure the time and intensity. Using those two things, we construct an image of body. I include very simplified version of the ultrasound machine, like because for Ravindu has included a very complicated version of X-ray machine. But here the main components you want to know is like in the front we have inside the probe we have a tiny speakers and microphones, so they can emit sound waves and hear back, and then those information goes into electronic part, and they control those speakers and microphone information and generate the image, and finally they display it through a display. Here I have added this, like I think most of you know the ultrasound probe, and inside that one we have these components like a matching layer, electrodes, and this highlighted part, piezoelectric element. That's the part of the ultrasound probe which act as the speaker and microphone. It can act as the both things. So why I have included this here is because one of the main limitations current ultrasound systems, I think most of the Sri Lankan hospitals have these kind of probes. So these kind of probes have one big limitation, making it bulky and not so like portable, because these piezoelectric elements, we cannot manufacture them as very tiny elements, and it's very expensive. So, but I think 10 or 15 years back, they have discovered that we can make these kind of like speaker plus microphone elements using some other manufacturing technology, which we use for manufacturing our chips inside our mobile phones. That's a very scalable technology and very cheap. So I'll talk about that again. I think in next 10 to 15 years, all of these kind of probes will be replaced by that novel technology, and it will be very cheap. Most of you can have your own ultrasound device. In this slide, so ultrasound is very good for detecting static things, right? We can send sound waves and hear the reflection and measure the time and what kind of tissues are there. But if it is moving, or like mainly blood flow, it's shown as a very dark area of inside the ultrasound image because it's not very dense material. So relative to bones and other tissues, blood and fluids are shown very in dark manner. So it doesn't provide any good information for doctors. What Doppler ultrasound do is it measure the using the Doppler phenomenon. I'm not sure whether you remember it or not, but during A-levels we all learned about Doppler. So if the object reflecting that sound wave is moving toward or away from us, there's a frequency shift. Based on that, we can identify whether the blood flow is coming toward us or away from us. Yeah, I think you get the point, right? If we don't have Doppler ultrasound, what we see is this darker region, but that don't give us any useful information. Instead of that, if we have Doppler ultrasound, we can get somewhat useful information.
Shouldn't it be blue towards and red, like in the context of astronomy when we are measuring like the galaxies and things like that? Usually when measuring their rotation, if one end of the galaxy is moving towards us, it's blue shift, and if it's away, red shift. So
Mhm.
what's the opposite in this ultrasound?
Yeah, like we can use either way. Like if it's in the standard way, it will be easy for everyone. But I think in this slide they have used it switched. Yeah. Now I'm going to talk a little bit about future of ultrasound. This is one device I found online, and here, so compared to traditional bulky device, they have only very small ultrasound device, and you can pair it with your mobile phone. And yeah, so it's very easy to use and very cheap. Also, this company, they provide a software. In that they are using AI and image processing to add anatomical information to the ultrasound image. So here in the left side, it's only the ultrasound image, but using some processing and artificial intelligence, they add more information which are pre-stored in their software. Yeah, and in this app, they are using AI algorithm to detect blood clots using ultrasound images. I have selected only few examples about like which are already in the market. You can see about more examples if you like. This one is not really about imaging, but I'm really excited about this application. It's about focus ultrasound. So when we focus ultrasound, we can like get very intense energy to a one point, and using that energy we can like interact with tissues. One obvious thing is if we concentrate any kind of energy, the temperature of that region will go up. So we can do thermal ablation inside. They are actually using that to like thermal ablate tissues inside the brain, mostly cancer tissues. And yeah, the second one is opening the blood-brain barrier. So we inject some medication into the bloodstream, and then we only open at specific locations inside the brain using focus ultrasound. We open the blood-brain barrier, and medications go into the brain. And third one, C, is neuromodulation. When like if a patient is suffering from a stroke and he's going through rehabilitation process, to speed up the things, we use neuromodulation. to that, there are two kind of things we can use mainly, either electrical stimulation or ultrasound stimulation. That's one thing you of focus ultrasound. Yeah, and yeah, this one is a very cool application, I think, because they have injected medication which are in a form of nano bubbles, and when they travel to a desired location, we use focused ultrasound to break the nano bubble and get the medication out only within that region. And last one is we can use focused ultrasound to build up small air bubbles inside tissue. So these tiny air bubbles act as tiny bombs. So they damage the tissue, and we can use that for to attack cancer tissues. Yeah, if you are interested, you can see more applications of this focused ultrasound. It's really cool.
Yeah, hopefully we can continue directly. Thank you, Hansa. And so I'll be talking a little bit about magnetic resonance imaging and nuclear imaging. So just to give you a heads up, both of these are like worth maybe like couple hour lectures. So I'll be going through a very basic idea of the MRI and a little bit more in depth with nuclear. So with the MRI, it uses magnetic fields and radio frequencies to get some sort of signal which can be interpreted into an image. So the fundamental principle is called nuclear magnetic resonance, NMR, and it can capture either 2D or 3D images with no ionizing radiation. And it has excellent soft tissue contrast. So this is a very important thing when it comes to MRI. You might have seen like the amount of noise, the amount of what do you call it? The resolution is much higher when it comes to MRIs. So there's no penetration effects, and so you can see the resolution less than 1 millimeter. So the quality of the image. So talking about the basic functional blocks of the MRI, I'll come to this. I'll tell you how it exactly works in a very basic sense. What you have are like our body has, let's say, water molecules. Those have the hydrogen atoms. Those hydrogen atoms can be they have some sort of magnetization, and we can give a large, more than I think half Tesla. Once we start above that, so let's say 1 Tesla. Once we give a 1 Tesla magnetic field, we can orient all the hydrogen atoms so that the magnetization is to a certain direction. All in the sense, again, you might remember from A-level chemistry, there are always exceptions. So there are going to be some ones which are not oriented in that direction. So for now, we have a magnet which we use. This is a ideally a permanent magnet. So what we have is a superconducting magnet which creates a strong uniform magnetic field throughout the body. So it orients all our, whatever the part of our body is within the scanner, to a certain direction. All the water molecules and some of the fat hydrogen atoms as well. So then what we do is we use this RF frequencies, radio frequencies, to change this orientation to a certain angle. So in our sense, we'll be using 90 degrees. So assume that all are oriented upwards at 180. Then we give it an RF pulse, so radio frequency, a radio wave, so that this changes direction. So radio frequency is an electromagnetic wave, so that can affect it. So this now turns sideways, let's say to 90 degrees. Now these do have a certain spin to it. So spin as in it keeps rotating. It has certain energies. So we'll just keep the rotation aside. It now is at 90 degrees and is rotating in this plane. Now we let it go. When we let it go, it starts coming back to its original point. So what we have is, we had it at 90, so let's say 0, we sent it to 90, and then we let it go. So by the energy we can, like once it gets back, it comes back in some sort of like a rotating pattern, and that releases a certain form of energy. And that energy is what we detect. This is in the form of electromagnetic waves. So these RF coils can detect that as well. That's detected, and the image is formed. So a very basic scenario is that. So I talked about the magnet and the RF coils. Then there's something called the gradient coils, which can be used to get the like. So you might notice like all the part inside the scanner gets converted to the magnetic field. Then it's under the effect of the RF coils. Then it comes back. So we don't want that to happen. We need a certain part of the body. So we need a slice, right? You might know what a slice is, a certain part of the body. So if we need, like, let's say, like some sort of a middle part of the brain, head. So what we'll be doing is we use these gradient coils to create some sort of variable magnetic field across the body. So let's say the magnetic field intensity here is half Tesla, here it's 2 Tesla. I'm just randomly saying. So if we want something somewhere here, let's say we'll consider only the magnetic field intensities of about 1.8 Tesla, something like that. So we use these gradient coils for getting these slices. So just a round up. So magnet used to create the magnetic field, gradient coils to select the slice, and RF coils to generate the extra magnetic field and to obtain the noise, obtain the signal. So we have a detector and source for the RF coils and a gradient generator. So that's that for MRI. I'm sorry I had to run through, but that's with the time constraints. So talking about nuclear imaging, this is a bit more simpler, because now that you went through CT, it's kind of similar. It's not the exact same thing, but it's quite similar. So here what we have are two forms, SPECT and PET. So single photon emission computed tomography and there's a issue here. So this should be a positron emission tomography. Yeah. So it SPECT is generally you have a radio tracer, and they generate gamma photons. So these can be detected. Or for PET, which is quite more common, I guess, and they generate gamma radiation. So in the form of positron electron annihilation. So you know annihilation, when antimatter and matter collides, it generates an energy in the form of electromagnetic waves. So now what we have is, we generally don't have these positrons in our body, so we have to send it through. So we inject an isotope. So commonly it's fluorodeoxyglucose, so FDG, some sort of isotope which does generate these positrons. So once we do generate these positrons, there are electrons in the body wherever these go and just stop at, and then they will start annihilating. The moment they start annihilating, 511 kilo electron volts will be released. So in like a perpendicular direction. So this released positrons will be then there's a kind of a ring around the body which will be detected by these things. So Ravindu mentioned something called a scintillator. So we sometimes use scintillators, and more modern, I think they use a form called silicon photomultiplier tubes. So there are different forms of detectors to detect these electromagnetic photons. So you might see so this is something interesting about detection. So these might not exactly match. So sometimes you might notice that this is kind of the case we want. So if it goes this way, the other one should go the other way. But sometimes due to like material differences, whatever it is, it could turn around, it could hit something, whatever happens. So what we need to know is, if something occurs, if we know that there is some sort of incidence, we need to confirm that it is due to the annihilation, and also we need to confirm that it actually happened at this point or within this line, let's say. So for that, what we do is we consider, so we have like numbered the detectors. So it's not just 16, but there's probably much more, but for our ease of use, it's 16. So once we do detect at 2, what we'll check is something on like the other side, whether something detects it. So 10 does detect it, so we know which line it is at. And then what we do is we add all of these together. So the signal at that point gets increased once you detect it. So when we add all those together, you can notice that at these in coincidence points, there's a small peak. So that peak is what we consider as a coincidence. So now let me go a little bit in detail into the latest developments. So this is something that is quite interesting when it comes to MRI. So MRI is what, as you might know, it's quite bulky. So there's a lot of like pipes, there's a lot of like there's liquid helium in it. So you have to replace that time to time. So liquid helium is used to maintain the superconductivity, which is used to in turn to maintain the magnetism. So you might know like 1.5 Tesla, 2 Tesla, maybe I think 3 Tesla is available here, right? I'm not exactly sure. Yeah. So 3 Tesla is available here. So what 3 Tesla can give, 1.5 Tesla cannot give. And what now the current research is into 7 Tesla scanning. So we have much high resolution scanning. So this is generally for brain only, neurological applications only currently. And so 7 Tesla scanning is not exactly possible with purely helium based cooling. So this is because the pressures and the temperatures that are required to maintain it at, then it will make the systems much more bulkier. So for that, so these two go kind of together and even separately as well. So we have helium independent magnets. So this is very interesting area. So I think Siemens have introduced a technology called dry cool. So very recently, where they have, so this is their prototype. So this has, I think, a very small amount of superfluid helium. So liquid helium initially, and then it just they don't use it anyway. So helium independent magnets, these can be used. So you might know like portably MRI is a bit of a hassle as well. There are some devices, but not very commonly provided. So portability is very useful, these helium independent magnets. Now also I also mentioned about this gradient coils, varying the gradient at different parts of the body. So imagine like you had something that could be worn. So that was, this is a very, still very much in research. So what they have done is they have a wearable system which provides these gradient coils. So it's called metamaterials. And so what you can do is generally now their experimentation. So you don't need the entire slice of this part. You don't need, these fingers won't be detected. Only these fingers, this part can be detected. Ideally in the sense once this gets through. So for much higher resolutions, for much higher efficiencies, this is a very interesting area of like MRIs. So as always, I think Ravindu mentioned this as well, there's always the machine learning part in it, there's always the image processing part, but when it comes to acquisitions, still there's much room to improve. So MRI, these are the areas. So when we talk about nuclear, now as I mentioned, I talked about FDG, so fluorodeoxyglucose. So that's a very common tracer. So these now what scientists are doing is research into, like, pharmaceuticals has gone like much further than FDG, where they can target specific biomarkers and like specific cancers. So like I saw something just works for breast cancer within, I don't know, like 45 to 60 years only or something like that. So very specific and very accurate. So these can be used for targeted biomarker tracing. So if you need some sort of like So this is something I read. I'm not exactly sure as to exactly how it all works, but if you have a patient with a lot of like a very highly spread cancer and you need a certain part of it to be highlighted, that can be done. So this resolution modeling is a very yeah, so resolution modeling is a processing technique where they have, so you might know when it comes to PET, it's not that accurate. So it's not, it doesn't have a very high resolution. It's quite a low resolution when it comes to PET relative to, let's say, MRI. So what we need is to get PET to a certain extent, at least comparable to an MRI. So we have a format, like this is a mathematical model where they use something called resolution modeling to provide higher resolutions. And also you might have heard of PET CT, SPECT CT, so quite common. So PET MRI is something that's also not widely available, quite available. So this now instead of using CT, we can use a lower, not lower, like non-ionizing radiation. Yes, there is of course the PET effect, but like at least the CT effect is lowered. So reduced radiation exposure and higher resolution compared to CT. So those are the parts when it comes to nuclear imaging what are being developed. So if I just give a small summary, the radiopharmaceuticals, there's quite a lot of research going into it. So when I looked into this, so that was what they were mostly focusing on, like radio tracers, different radio tracers for different biomarkers and so on were the major focus area. So yeah, that's the end of our session for the medical imaging modalities. Are there any questions so far? No, yeah. So I think we'll continue, right? Yeah. So continuing on, what I'll do is yeah. Yeah, sure.
Thank you very much. I have to go off in a little while, so I thought I'll give my 2 cents worth. Ultrasound, you were mentioning about ultrasound now. One interesting area is which we are working on is to look at 3D imaging using the routine ultrasound. The routine ultrasound gives us a 2D image, but whether we can develop a 3D image to measure the volumes of organs. So right now there is work being done in Sri Lanka, and some of it is being done in this faculty. Of if you should meet those who are interested, go and meet Prof. Udari Liyanage in the Department of Anatomy, right? So the idea is to see whether we can measure the volumes of liver and the kidneys using the routine ultrasound, but with other cloud-based algorithms, etc. So we are working with a team. I don't know whether you know Zone 24/7 Zone. So that's the team which is helping, and we've been having weekly meetings for the past 2 or 3 years to get an idea. This was an idea which I proposed long time ago, but to get an idea into commercial level takes months and years. Right, so that's what to do. We haven't. The systematic review is being done on imaging, ultrasound imaging in volume assessment. Then we had to compare CT measurements of volume with the ultrasound measurements, and so a lot of work. So that's one. Second thing is these 3D reconstructions. Those who are interested, you all should visit the radiology department, right? They do all these reconstructions. Even I mean, the reconstruction images of kidneys, liver, gallbladder, I mean, it's fascinating. It's fascinating. It's available in Sri Lanka. Unfortunately, most instances we are shown in our medical lectures, you'll be shown images of x-rays and angiograms and so on. But the 3D imaging is there and it's amazing, right? If you want to study anatomy, you should be looking at some of those images. So that's in relation to this reconstruction. Of course, from a medical point of view, there are various new things. Now, cardiology, they are having the, in addition to the usual coronary angiogram, now they have the CT angiogram. So you give a small volume of the dye and you reconstruct the whole cardiac image with the coronary arteries. Done in Sri Lanka, right? MRI of the heart is now being done in some of the private hospitals, because when you look at the echo, which is using the ultrasound technology, you are seeing the chambers. You can use the Doppler to look at the blood flow, but to look at the structure of the muscle, you can do the MRI, because the MRI will tell you when there is myocarditis. So we recently had a patient who was having a myopathy, inflammation of the muscles for the medical students, right? And the CPK was 30,000. Patient was complaining of shortness of breath. So differential diagnosis includes muscle weakness causing difficulty in breathing, whether it was a pulmonary fibrosis associated with an autoimmune myositis, or whether there was heart failure. So you do the echo and you find the ejection fraction to assess the motion of the left ventricle to see whether there is heart failure. And by the way, ejection fraction 60% is normal, right? 60%, because it's a fraction, no? But patients get very worried because they think their heart is functioning at 60%. It's a different story. But so ejection fraction was okay, but we wanted to see whether there was myocarditis because the troponins came sky high, right? So then we did a MRI of the heart. Okay, so I think, you know, those of you who are interested, just visit some of the radiology departments, speak to them, and you, if you are interested in imaging, there's so much which is happening. And if you find, I mean, ideally is the National Hospital, there will be people who will teach you all. Go to some of the private hospitals because they have more time. You see, these private hospitals, they have more time. Here you are clearing crowds now. So if you have a friendly radiologist or even a radiographer, they will tell you a lot of aspects related to these imaging. Yeah, so thank you very much once again. I have to go now because I have something more tomorrow early morning. I have to leave. So thank you once again. I think it's fascinating. Thank you, Mora, for coming.
Before we move on to the next session, I think we should all thank Prof. Saroj for gracing us with his presence. So thank you, sir, for coming.
I think I'm audible, right, to everyone? Yeah, so, we'll be going on to the practical session, so if there's anyone who will be following, do you? So I think you have access to the files that was sent. Praveen, is that the case? Files. Do they have access to the files? No. There's another chest X-ray and a brain proton density slice. So with these three images, two images and a file. So what you can do, so as you all may not have a code editor, so you can go to Colab.research Google. So you can just search for Google Colab. So not collab with 2 L's, just 1 L. Colab, and once you get here, just let me know. Once you have downloaded the files and got to this page, just let me know. So is everyone cool with this? So got to this point? Yes? No? No. Okay. So yeah, if there's anyone using VS Code and is comfortable with it, they can follow with this. But I just went with Colab because it's simpler if you don't have any editors on your laptop. So once you get here, you can upload the notebook that was provided. So that ends with IPyNB, workshop 1 codes. So you can upload that there. And so you'll come to something like this. Guys done? Yeah. So then you can select runtime and change runtime type. So you don't have to give it just, or you can just select connect on the other side. Just give it CPU, that's enough. You can select connect here as well. Because we don't need a GPU, we can just give connect as well. So yeah. So once you're connected, This is the last part. So you can see on the left hand corner there's like a file icon. Click that, and there's an upload icon. Then you select the two images. So here. So you'll get a warning that it only stays with the runtime. For now, that's more than enough. So you only need one runtime. So once you get to that point, so these code blocks you can just run one by one. Just the first three. So you can run the first, second, and then the third, and just check whether you get an image and something else. So if you do, we are good to go. If you get this, all's good. So is everyone good up till this point? Does anyone need more time? If you need more time, that's fine. Yeah. So if you are just getting that set up, that's fine. I'll go to the slides. So yeah. So I'll talk it with this. So generally, when it comes to medical images, they are in a format called DICOM. Can't remember the terminology, but yeah. Here I have given you PNGs, which is the easiest form for us to manipulate, but it is not what we work with, so we need extra libraries for that, so no need for the hassle. So what we'll be having are black and white images. So black and white images are generally notated with every pixel given a color, like color value. So this value is an 8-bit value. 8-bit value means 256 values are there. So you might notice like 0 to 256. 0 will be fully black, while 255 will be fully white. So black, white, and then there's 254 shades of gray, not 50. So now this image, you might notice, so with it is considering the edges as well. In this whole image, you might notice in the initial part, like between like maybe 0 to 25, much darker region, there's a lot of pixels. So this is a histogram. Histogram is a notation of how many pixels of each intensity are there. So here you have between like 0 and 25, there's quite a lot of pixels. So that's these edges and then the skull. So then the middle part, there's not a lot, and then there's a little bit of like lighter grays and whites are also there. So that's a very basic interpretation of the image. So we have 0 to 255 notated here. Now if I go to the slides, we'll be going through very basic image processing techniques. So very few of them. So because when it comes to, there'll be a small machine learning part later as well, but it's not very easy to do hands-on machine learning within like a small time. You need like couple of hours for that. So we'll be going through some basic image processing techniques. These are called point transforms. So point operations. So you consider each pixel and you do something to it. So transforms are just some sort of operation you are doing to it. So you might notice like here it's just input and output. Whatever the value, it's mapped to the same value. So if you have 150, it will be 150. input and output is the same. Now what we are going to do is we want to determine if we want to separate something. If we want to, like, for example, in the image, if we want to separate out the white matter from the gray matter or something like that, what we could do is we could set a threshold at some point. Anything lower than that is set to black, 0. Anything above that is set to white. So this is called binary thresholding. This is a very basic form of thresholding. So what I want you to do is go to the code, and you'll notice the fourth code block, point operations intensity transforms. So you can try to get me a value here that gives a nice separation for the gray and white matter. Whoever gets it first will get, I don't know, an extra drink. So I'll give you a hint. So as I mentioned, this is the background and the skull. This is mostly the gray and white matter together. So what you need might be closer there. That's a hint. So you can just try to think of a value. So what we are doing is mapping one edge to white, the other edge to black. Also, yeah, so someone figure it out. We'll see what the value is. So yeah, if there's any questions with regards to what is going on or anything, you can just ask. If whatever I'm saying, you can just ask, or else if there's any help you need, you can ask from the ones close to you. You can just try different numbers randomly, just type it out and see what happens. Okay, did all tables get a number? That's done, right? That's done. They are done. They'll get an extra drink. Okay, can someone tell me what the value is you set? Anyone? 180, okay. 187. Maybe a bit high, let's see. 170? 178 was what I came with. I didn't give the code, right? Okay, I'll try 180. So 178, there's 178, there's 187. Let's say 185, 183. Okay, now I'm giving it an average. Not bad, but not great. So you might notice a little bit of the whites are missing. So what I'm going to do is reduce it slightly. Let's say 176. So you can play around with this. You can change these white values to a little bit of gray and figure out what to do. So you might notice again a little bit lower. So 180, 179, something like that would be much nicer. So all we did was set one edge to one point and the other, like points beyond a certain value. So here 179 in my case, above that to a certain value and below that to another value. So if you have time, you can just give that image here and check. So I'm not going to do that. Now, so now I'll go to another small interesting part. So this is a bit too rough, like this shape. If you notice, is a very sharp thing. So what do you do if the value is 178, whatever we are figuring out? That's ugly. We don't know, it goes to 1, but we don't know whether, like, it goes to 255, but we don't know. It's ugly, it's not smooth. So when it comes to stuff like this, operations, mathematical operations, it's not very easy to do. So when it comes to things like this, you can't differentiate, you can't integrate, it's ugly. So what we are going to do is we are going to get something beautiful. So this is called the sigmoid. So the sigmoid function has 2 parameters. So one is the midpoint. So the midpoint, at which point it's cutting at. So just imagine whatever we had previously. This the red line is kind of like a midpoint. And then how steep it is. So you can notice, like, blue is less steep. We have a lower alpha value. This beta value will be the center. So we have 2 parameters, alpha and beta. So you can notice, like, alpha increases, the steepness increases. So you can, so ideally if alpha goes to a very high value, so here then it will be close to what we previously had. So I have given that as well. You can try that out as well. So give me an alpha and beta value. So there's 2 things to figure out, maybe 2 drinks. All right, so as we had 178 previously, 179, let's say 178 here, and I'll have a steepness of maybe, so here the alpha is not exactly like in decimals, so let's say 8. Yeah, so I can just change these values and check if we are getting something a bit nicer than the previous. So hopefully you can figure that out as well. So now I'll move on to region-based methods. Now when it comes to an image, so when we apply on areas, so we need something called a kernel. You can write on this, right? Yeah. So hopefully this is visible to the guys there. I'm not sure exactly whether it will be. Yeah. So a very basic thing when it comes to images, we can consider that to be some sort of like grid of pixels, so on and so forth. So when we apply region based things, when we want to apply, like previously what we did was we considered each and every pixel. Now what we want is we need its neighborhood. We need to know some sort of like other information from around it. So what we'll be doing is we'll have something called a kernel. So that's another square with some sort of values at, let's say, around it. So we can have 3 by 3, we can have 5 by 5. So we'll have a pixel, and around it we can have several layers or so. So here we have a 3 by 3 kernel. So only this and then around it. So what we'll be doing is we'll be moving this point, this x, at each keeping it at each point and considering the value. So whatever we are doing, we'll be doing on it on this region. So that's what is called a kernel. A kernel is basically a set of pixels, not a set of pixels, set of numbers in the form of a grid. So that grid we can place it anywhere with the center on whatever pixel we need to consider. If we need to consider this y pixel, we can keep the center there and form a grid and then do whatever we want from there. So what I have done is a maximum filter. So here what we have considered is we have considered this pixel. For this pixel, whatever we are doing for this pixel, we consider this whole region and consider the maximum intensity. So maximum intensity in the sense of 0 to 255 is the lightest pixel, right? On this, the maximum will be this pixel when it comes to intensity, and then we have replaced that with this. So if we go from top to bottom, it will be a bit lighter image from top to bottom. So I have only replaced one. So when it comes to filtering, so filters are basically, you might know, like when it comes to like physically, it's removing stuff we don't want. So filters are used to remove noise, other forms of effects. So you might notice like there's a weird image. What I'm doing is considering, so this center pixel, only on this center pixel, what I want to do is filter it. So what I'm doing to filter is one by mean, the other by median. So I'll mention why later. So we have these values. So you can notice earlier there's 67, something, 78, 9, 216, so on, so forth. So we have values. So we take the mean of these values and replace this pixel. So that's what's been done here. So you might notice like the color has varied. And then on the other one, we have taken the median. So earlier it was 195. In mean it's 146, and then the next one it's 179. So you don't have to go much into detail, but you might notice that there's a filter that I have shown here. So we have a noise added to a purely gray block. We have applied mean filtering. I don't know if it's very clear here, but it has kind of blurred it out. That's all that has happened. Kind of blurs it out, nothing happens. But when it comes to median, most of the time, if the randomness is not too awkward, you'll get a almost pure gray. So median filters work well with noise opposed to mean filters. So you can, once you go home, you can run it a few times. You can increase this salting and peppering values or decrease it or whatever, like here, sorry, here. So these two values you can vary. You can vary the kernel size. So I have given 3 by 3. You can set it to 5 by 5, 7 by 7 and see what happens. The blurring will increase and so on. So I have applied the filtering on the images as well. So on your screens you will notice it a bit more clearly. So you'll notice the median filter is a bit more lighter in color. It's a bit more sharper. When it comes to the mean, it's slightly blurred. So this is not super important when it comes to MRIs. Quite important, but not very important. But when it comes to X-rays and stuff, removing this noise is very important. X-rays, CTs, ultrasound, very important. So when it comes to anything that has a lot of noise, this can come in handy. So moving to the last part there's one more part. So then we have something called edge detection. So you don't have to worry too much about this. So I'll just talk about a very basic form. So you might notice now, like let's say I'm plotting the value of the pixels. So you might notice like here, if I consider this point, it will be close to 255. Moving forward, it's still 255, 255. Now it's going to drop like maybe to like 50, 60. So these high change. So when you go along this line, you are seeing a very high difference at a certain instance. And when you do see these high differences, that's called that's considered to be an edge. So you might notice if you like these corners, edges in both sides, there's stuff like that. So there's something called an edge detector. So there's different algorithms applied. Something called edge detector. So what we are doing is, when we apply an edge detector, we first blur the image a bit because noise can affect this edge detection highly. So we blur it, and then we set these two of these limits. So I have just given these. You can try out different values to these limits. So you can just vary these upper and lower limits and see what happens. So you might notice like on the chest X-ray, I have given some values so that we get a certain like number of edges. So you might notice if you reduce this upper threshold a little bit, the image that you'll get is going to be different. So now you have much more edges. So this depends. This is like visually is the best way to figure out what's the best kind of number. So I just went with 10 and 50. All right. Then there's something called a Sobel filter, where you can just take the horizontal edges or just the vertical edges. So I don't think this is very clear, but it will be a bit more clear on your screens. So in this horizontal one, what you'll see are like kind of the vertical edges, and on the vertical one you'll see kind of the horizontal edges. So when it comes to edge detection, it's a bit difficult to explain like in detail. So we'll go to this morphological operation. So this is another very interesting part that has been used in the deep learning example as well. So now when it comes to morphological operations, again we have kernels. So we have this part which we are considering, and when we come to this pixel, what we are doing is, we have two forms. We have something called dilation, we have something called erosion. So you know what dilation is, we are increasing the size. Erosion, we are decreasing the size. So in this, what happens is, if at least one of these pixels is white, we are considering these 9, at least one of these is white, then it sets this part to white. Whenever it's anywhere, if there's any pixel that's white, it will consider that center pixel to be white. So because of that, this dilated image will be a much larger image. For erosion, it's the opposite. For erosion, all the pixels should be white. So here, when we are considering this center pixel will not become white because these parts are not white. Not a racial thing, but yeah. So if you move it to the center, then all of these will be white. So the eroded image will be white. So this can be done both on black and white, but I have done it on white because it's a bit easier for my example. So one last time. So for morphological operations, I've shown I've used an intensity transformation on the early image and then applied erosion. So what you can try is to change the kernel sizes. So I have set 5 by 5. You can set it to 3 by 3, 7 by 7, whatever. You can check that value, what happens. And then number of iterations as well. You can check when you set it to like maybe higher number of iterations, what happens? So an iteration is how many times you're doing it. So you erode once, you erode another time. So here I have given it 5. So erode continuously 5 times. So then you get much smaller image. So this is useful to like remove like unwanted noise. So this is not a very nice example, but yeah. And then one last thing, I have dilation. So you might notice that this is much clearer than the other one. So what we have done is to like kind of thicken. So dilation is very useful to thicken the ones. So what you could do once if you are interested, is to apply dilation and then erosion on this. You might notice something very interesting. You will like edges, like just like points and stuff will vanish. So it's very interesting when it comes to dilation followed by erosion, erosion followed by dilation. There's 2 operations called closing and opening. I'm not going to talk about it, but yeah. So these are not just applied on its own, but sometimes in combination with others, and so on. So yeah, that actually brings me to the end of my session. The image processing part, you can go through. If there's any questions, you can ask the ones close to you, or you can ask me. And Ravindu will continue on with the rest of the basics of deep learning. No questions, right? Cool.
It's a bit uneasy to stay here. You have been here about 2 hours now, so I'll finish this off quickly. And the goal of this part is give you a basic understanding about that growing trend AI and machine learning stuff. So and how it work in the medical domain. So first I'll give a brief introduction about what is the deep learning and machine learning, and next we are going to explain a project that we have done by using this AI based medical image classification. Okay, so first let's go about I think you have heard these terms, machine learning and deep learning. Actually the machine learning is something we call a statistical type of learning. Statistical mean like we are doing a lot of things with statistic in machine learning, and deep learning is basically a probabilistic learning. Probabilistic learning means we are going to like predict a lot of things. Actually we are predicting a probability. If we have a picture, let's say we are giving a probability of that picture to be eat a dog or something like that. Okay, so actually these are the things that we are AI. AI is a very large area. These are some subsets of AI. So when it comes to the deep learning, the first thing is neural networks. You know neurons, right? Our brain has built up with neurons, right? So in here also, the neuron is something like our brain cell, artificially made brain cell in our processors, right? So we have connected them, like you can see here. This is a neural network. So these are the neurons. So there are 3 layers. So these are input layer, output layer, and there are we call hidden layers. So we have connected those in our brain also. The neuron has connected, right? All are connected. So here also we have connected neurons, and after that with the input and out, with the input we can take decision what is the output. So actually there is a pretty interesting thing. So we know this input is, if we given an image, the pixel of image, and output is a label or some prediction. So what is the middle part? So actually we say we are doing feature extraction and some other stuff. So there are the middle part, actually we call it hidden layer. So people are doing research about to interpret what is the hidden part here, the middle layer. We can design the network, but people will, scientists say people will never know what inside the hidden layer after we train a network. Okay, so it means there are dimensions that more than 3. Let's say 128 dimensions, 512 dimensions. So people will never know what inside this hidden layer, right? Okay, for now, maybe in the future researchers may find something. Who knows? So okay, so in a neural network, as I said earlier, these neurons are connected together to make a decision or predict something. So here you can see I have mentioned a neuron function. This neuron function is, we have assigned a weight to each of these neurons. Weight means like let's say 1, 2, 150, 41 or some values to these neurons. Then with this input, let's say we give 1, 2, 3, 4, 5. This has connected to this neuron connected all these values. So we multiply all the value with weight of this neuron. Then we take output. Then we took this output with activation function. So there are a lot of activation functions. So no need to go in depth. I just explain what is the neuron and what is the neuron function. So these are the basic building block of a deep neural network, right? So okay. Now let's go to the convolution neural network. So when it comes to the convolutional neural network, we call it CNN. These are the neural networks that we are used for image, video, and like spatial data, like 2D like data. Okay, 2D, 3D data. So here what happened is, Senul explained kernel operation, right? Can you remember that? Yeah. Okay. I think I can explain it here. I think you can remember what is a kernel. Kernel is something like this. I'll draw a 3x3 kernel. In a convolution neural network or CNN, we design kernels based on our knowledge. Researchers have designed kernels. So I'll take a random kernel. Let's say 1, 1, 1, minus 1, minus 1, minus 1, 1, 1, 1. So when we took an image, let's say 512, 512. This means there are 512 pixels in this side and 512 pixels in this side, right? So let's take this. So what we do with this kernel is, we place this kernel in here. Okay. Then there are some values in this image, right? As Senul mentioned, 0 to 255 values in each box. Let's say 86 or some random values. So we place this kernel in here and take this multiplication and build another image. So in here, the value in here now is in here, right? So after that, as you can see here, this is the image that we took, and we took the kernel operations. Then we form another image. Then we do something called max pooling. Max pooling, like not actually max pooling. We call this pooling. There are max pooling, min pooling, average pooling. So it is like there another kernel like this. So we place it in here and take the in max pooling, take the maximum value to outside. Okay, so now you can understand when we go forward, the image sizes get reduced, right? Because we took 1 pixel, something like that. So here also you can see we have this image. So by using kernel operations, we took this one, then max pooling this one. Again we do kernel operations. Likewise, we go certain amount of layer. The designer can decide the how many layer, the number of layers, and finally we use the fully connected layer. Fully connected layer means a layer like this. So every neuron is connected to the next neuron. Okay, so that's the fully connected layer. Then we got output. So this is a basic idea of the CNN. So when it comes to the color image, the image is 3D, right? 3D means like a black and white image. It has the pixel like height and length. In color image, there are RGB, 3 black and white, like images like black and white, 3 images, right? So in that color image, we can design kernels like 3D kernels. Okay, like yeah, the dimensions of the kernel is also designed by designer. So this is a basic idea of CNN. No need to go very deep because it's not easy to understand some theoretical stuffs in here. So yeah, I think you got some idea about this. Any questions in from here? Okay, no questions. So let's move forward. So then we have something like loss function. So this is another tricky thing to understand. So loss function mean when we are training a network, you know, like in machine learning or deep learning, we are training a network, right? We are training a model to do something. Okay. For an example, we are training a deep neural network to localize some injuries in a brain, something like that. Okay. So when we train a network, we have to like give some input, like feedback to the network. Let's say we give some image, then we we say the network predict what is this. This is in training purpose, right? So then network give an output to us. So when after seeing that output, we say no, this is not the preferred output. This is the preferred output. So rearrange your weights to give the preferred output. So likewise, we do like forward and backward propagations by using these loss functions. There are few type of loss functions. Regression purposes means like let's say you have data like land size, distance to the main city, and house price. Okay, when you give the land size and the distance to the main city, the model will output the price of the land. So in that case, you have to give a certain number, right? This is the number, like this is the price of the land. So in such situation, we call regression. When it comes to classification, it's like by giving a medical image, like MRI, we are going to localize whether there is a abnormality in the image. So such cases is classification. So for those situations, we use this cross entropy, hinge loss. There are a lot of loss functions. So I'll explain what is the most important loss function in medical image processing. This is the basis for most of the loss function that used in medical image processing. This called dice loss. It is like I don't know whether you can understand this or not, but try to understand this. So let's say when it comes to a deep neural network training, we have a data set. Data set contain, let's say, MRI images with brain intracranial hemorrhages, right? So there are hemorrhage type and MRI image. So we have to create a data set by annotating where is the location of the hemorrhage. So by giving that, we can train our network. So in such situations, when we training, as I said earlier, first the network predict an output. So there is a ground truth. Ground truth means actual output in the image. So the dice loss is taken like intersection over union. Intersection means how the predicted and ground truth value amount of overlap between predicted and ground truth value over predicted value and ground truth value, like union. Okay. So if you play around with, like, think about this, you will understand when there is a perfect alignment with predicted and ground truth value, the loss function will reduce. So just think about that when you are at free time. So I'll not going to explain it more. Okay, now this is the training phase. As I said earlier, this is our neural network. When it comes to the training phase, we have something called forward propagation and backward propagation. The thing is, in deep learning and machine learning, there are heavy dose of mathematics. All are based with mathematical operations and mathematical theories. So try to understand if you can, if you really wanted. Okay, I'll explain very simple way. So this is the thing, when forward propagation, I said earlier, in a training data set, there are two things: images. I'm going with medical images and labels. Okay. So first we give images. Images are given as numbers. As Senul said earlier, every image represents with a grid of numbers, right? So then we say to model to predict what is in this image. So model gives a prediction. So they give prediction based on these values. Okay, based on these values, I said earlier, we have assigned values in here, like 1, let's say 10, 12, something like that. So every neuron have value. So then model predicts something. So there is a true value. Then by using our loss function, we tell the model there is loss in here. So model does do backward propagation. In backward propagation, what happens is, there is assigned value in these neurons. Model try to adjust the value to give the desired output. Desired output means true value. So that's what happens forward propagation and backward propagation. Likewise, we do this forward propagation and backward propagation in desired number of iterations, maybe 10,000, 100,000, 1,000,000, like maybe a huge number of iterations, then we can have a desired model. Okay, training and inference process, as I explained earlier, training is what I just discussed. Inference means after we obtain the desired model, we can use that model to do our work. As you can see here, we have a large number of data set. By giving this, we train this model to predict what is in the image. Here we train giving this bicycle. This is a bicycle. If it predict it wrongly, we give there is error. Then model adjusts their ways to predict this as a bicycle. Okay. Then we in inference we give another picture of bicycle. Model correctly identify it as a bicycle. So these all happen with margins, right? Margins, there are accuracy in this model. So maybe it identify this as a bicycle in 90%. Okay, maybe 10% it will be maybe people or strawberry, but we took the most probabilistic item. Okay, so I'll explain what we have done in this domain. Okay, this is a project done by us for localized intracranial hemorrhage type using CT scans. Okay, so here's a CT scan image. So what our purpose was, by using a deep learning model, identify different type of hemorrhages. I think, as I know, there are 5 types of hemorrhages, brain hemorrhages, and external another one I don't remember. So we use BHX dataset. This dataset has, as I said earlier, 23,409 images, annotated images for training purposes. So there are 3 versions, those are not necessary. So here you can see these are the annotations, right? So this is a hemorrhage in here. So they have annotated this as a hemorrhage. And here. So yeah, these are 6 types of situations that they have annotated. I don't know, you know better than me, right? I don't know this stuff. Okay, so our purpose was identify these 6 types of hemorrhage by using deep learning model. So what we does is just like think we have data set, we can't directly feed them into deep neural network and take outputs. So we have to do lot of things before we train a deep neural network. So first thing, data pre-processing. It's like Hounsfield unit, right? Hounsfield unit are the unit that like contain in a CT scans. So there are Hounsfield number in for water and bones and something like that. So we have to do Hounsfield unit to pixel transformation. Then windowing means like Hounsfield unit had very big range, right? As I can remember, there are negative numbers as well. I don't know. And 5000 also is there. So very, very big range. We have to map them to 0 and 255 in our case. Then normalizing means something we do for generalized purposes. And morphology dilations, then we'll discuss this thing. And dimension squeeze means we have to reduce the dimensions for training purposes. So, sorry. Then we have to prepare these things for train and testing. The training means the process that described earlier. I think you can remember the forward and backward process. Testing means after we train the model, we evaluate the model based on the pre-selected data. So for that we have to split our data set. Here we have, normally we take 80% of the data set for training and 20% for testing. That's not a rule of thumb. You can change those values as well. So after that we employed this in a YOLO V8. This is a model, deep neural network model mainly for object detection. So there are a lot of more models like AlexNet, AlexNet, ImageNet or something like models. So people can use any kind of model based on their application. We use this YOLO V8. So in here we have our input image, then we pre-process those images, then we split our images to training and testing, then we train our YOLO V8 model by using those images, and we got our outputs. So I'll briefly explain what happened in our case. These are not necessary. So this is a ground truth. Ground truth means the medical doctors annotated images by using their hands. Means they looking at the image and they annotate those images. These are the bounding boxes given by our model. So closely observe those 2 slides. Maybe like there are almost only 1 or 2 errors in the bounding box in our predicted model. These are purely predicted by our model. I think there is faulty detection here and also here. Instead of those, all other things have predicted very accurately by model. These are model outputs from our project. Yes, these kind of things can do by using machine learning and deep learning stuff. So yeah, these are the applications in medical domain in AI in medical domain. So yeah, with that we can conclude our deep learning and machine learning session. If you have any questions, you can ask from me now. Yeah, feel free to ask anything because there are nothing, no one here to judge. Uh, Actually, yeah, part of is correct, part of is wrong. Highly complicated pattern machine. I'm not going to say yes or no, but I'll discuss it with you briefly. So let's say this is a very simple example. Let's say you have a x value. There are functions, right? Y samanai, sorry, y equals x square, something like functions, no? So there are x values. With this x value, there is a function like this. The function value varies like this. Okay? This is y. So I want an AI model to predict the value of this function with given x. Maybe here. Let's say x equals x naught. Okay. If I going to design a AI model, train a network for this, what is the network doing is it generalize over this data set. It means it it take the whole idea about the data set to its model. Okay. Always in a model has an error. You know this is a true value, right? In this x value, the correct y value is this. But in model predict it as this. There is error always in there. But what this machine learning or deep learning does is, it always generates our data set and give a prediction based on seen data. Okay. I think you got some idea about that. Is it okay? Okay, thank you. Is there any question? Seems do you have a question? Seems there is no questions. So okay, so then we can wind up our session for today. And again, I thanks for the science and technology community for organizing this workshop, and hope to collaborate with you guys again. So thank you.
So I guess that concludes the session, and it is my great pleasure and honor to deliver the vote of thanks for today's event. So first and foremost, my heartfelt gratitude to the three biomedical engineers who conducted the session today: Ravidu Pushpakumara, President of PFB's Motor, Seno Samarakara, and Hansamar. You guys did a marvelous job today, and you will be remembered by the medical professionals and medical students in the audience. And also those who are joining online. And also many thanks to the team from University of Moratua for sacrificing your valuable time and effort to help out in this event. The success of today's event would not have been possible if it wasn't for the valuable contributions of MFSTD committee, Rubik and the team from MFC ECHO. Even in the face of academic strain, you guys were committed to this. So thank you. I would also like to extend sincere thanks to the Medical Students Welfare Society and Medical Faculty Students Union for the invaluable support and seamless coordination in making this event possible. Finally, my gratitude to all of you who joined us today. Your enthusiasm and engagement was truly inspiring. So why MFSTC? What is the purpose? And don't doctors have enough to study? Not out of disrespect, we see the miracle of medicine every day in wards, but we also see the defects, areas of discrepancy. There are many questions left to be answered. There are so many ways our methods can be optimized. There are so many layers our understanding can go deeper. And I would argue that that is why medicine is such an exciting field of study. But to do that, we have to look at life medicine from different perspectives. What is disease? It is a physiology of the body deviating from homeostasis, as the doctor might see, or is it a defect in a control system like an engineer might see, or is it emergent complexity changing its state under perturbations according to a modern mathematician? Or is it a social phenomenon? Is it art or story? In my opinion, all these perspectives are true, but they are true only partly. It is only when they are integrated, a deeper truth, a deeper understanding would reveal itself. And this frontier of integration is the vision, mission, and the motivation of MFSTC. And the purpose of these sessions, to give novel perspectives that could change lives. So thank you for joining us today, and we hope to see you soon with a session on electronics, embedded systems, and biosignals processing with this wonderful team of engineers, and hope to see you all there. Thank you.